Hello, welcome back. So in this section, we'll talk about approximating functions with polynomials. Let's start with power series. What is a power series? A power series is an infinite series of the form the sum from k is equal to 0 to infinity, c sub k times x to the power of k, which will be equal to c sub 0 plus c sub 1x plus c sub 2x squared plus and the c sub n x to the power of n plus c sub n plus 1 x to the power of n plus 1 plus and so on. Or more generally, the sum of k is equal to 0 to infinity c sub k times x minus a to the power of k, where the center of the series is a. So on the first summation, the center is what? 0. Okay, when the center is a, we'll have c sub 0 plus c sub 1 x times x minus a plus c sub 2 times x minus a squared and so on. And the coefficients c sub k are constant. This type of series is called a power series because it consists of powers of x or power of x minus a. So let's jump and do some approximation. We'll start with linear and quadratic approximation. So, in chapter 1, in calculus 1, we learned that if a function f is differentiable at a point A, then it can be approximated near A by its tangent line, right? That's one use of the derivative, which is a linear approximation to f at the point A. So you need to know the linear approximation at A, name P sub 1 is given by P sub 1 of x is equal to f of A plus f prime of A times x minus A. So this is just like linearization in calculus 1. And the quadratic approximation at A, name P sub 2 is given by P sub 2 of x is equal to f of A plus f prime of A times x minus A plus the second derivative of f of A divided by 2 times x minus A squared. So I'm not going to do the proof here, but you can see this is just like what? P sub 1, right? This is P sub 1 of x that we have. Okay? So now let's jump and start some of the examples. So linear and quadratic approximations for ln of x. So find the linear approximation to f of x at x is equal to 1. So which means my a is 1. We can see I like to always write my formula down so I know what I have to look for. Is what f of 1 plus f prime of 1 times x minus 1, right? So we need to know f of 1. I'll take my scratch paper, or you can work. F of 1 will be equal to ln of 1, which is 0. We need f prime of 1, but to find f prime of 1, we first need to find f prime of x. F prime of x is 1 divided by x. So f prime of 1 will be 1, right? Therefore, my p sub 1 in this case of x will be f of 1 is 0 plus f prime of 1, which is 1 times x minus 1. So that means p sub 1 of x will be x minus 1. Sometimes they will ask you to sketch, if you sketch this one, this is the graph, the shape of the graph is what? Just a line. Okay. B, the quadratic approximation. So again, solution. So we know P sub 2 of x is what? It is, f1, because in this case we know f of a is 1, so it would be f of 1 plus f prime of 1 times x minus 1, and then plus 1/2 the second derivative of f of 1 times x minus 1 square, right? We have already done this one, so we know this is what? X minus 1. So we don't need to do that twice, right? So we already know this is x minus 1. So we need to find the second derivative of f. Or we can see the second derivative of x will be what? It will just be -1 divided by x squared. So the second derivative of 1, f of 1 is -1. So we will have p of 2 of x will be equal to x minus 1, then minus 1/2 times x minus 1 squared. And that's it, right? So now, C, use this approximation to estimate ln of 1.05. So to approximate ln of 1.05, we substitute x is equal to 1.05 into each polynomial approximation. You can see P sub 1 of 1.05 would be equal to what? Let me write each function that we have first, and then I would substitute. P sub 1 of x is equal to x minus 1. So which means P sub 1 of 1.05 will be equal to 1.05 minus 1, which would give us 0.05. And then the quadratic approximation P sub 2 of x is x minus 1 minus 1/2 times x minus 1 squared, right? So which means P sub 2 of 1.05 will be equal to 1.05 minus 1 minus 1/2 times 1.05 minus 1 squared. You use your calculator and you will see this one will give me 0.04875. So the value of ln of 1.5, use your calculator and see which one is it close to. So using a calculator, ln of 1.05 is approximately, in 5 decimal, it will be 0.04879. So the quadratic approximation is closer to the linear one in this case, right? So let's move to the definition of Taylor polynomial. So let f be a function. Let f be a function with f prime, f the second derivative of f, so on until the nth derivative of f defined at a. The nth order Taylor polynomial for f with its center at a, denoted p sub n, has the property that it matches f in value, slope, and all derivatives up to the nth derivative at a. That is, p sub n of a is equal to f of a. P sub n prime of a is equal to f prime of a, and so on. P sub n of nth derivative of a is equal to f nth derivative of f of a. The nth order Taylor polynomial center at a is p sub n of x is equal to f of a plus f prime of a x minus a plus the second derivative of f of a divided by 2 factorial times x minus a squared plus, and so on until the nth derivative of f of a divided by n factorial times x minus a to the power of n. More compact, p sub n of x is equal to the sum from k is equal to 0 to n, c sub k times x minus a to the power of k, where the coefficients are c sub k, which is equal to uh, k derivative of f of a divided by k factorial for k is equal to 0, 1, 2, and so on. So let's start with the first example. Find the Taylor polynomial p sub 1 up to p sub 7 centered at a is equal to 0 for science x. So solution again, I'm just going ahead because we are asked to find p sub 1, p sub 2 up to p sub 7. So let's find, we know a is 0, so we know we need f of 0. We know f of x is what? Science of x. So this means f of 0 would be what? 0. F prime of x is the derivative of sin x, which is cosine x. So f prime of 0 will be 1. We have to do all of this, okay? And the second derivative of f of x will be negative sine x. So which means the second derivative of f of 0 would be 0. The third derivative of f of x will be what? Negative cosine of x, so which means the third derivative of f of 0 will be -1. So you see, we will follow this pattern, right? After this one, we come back, the fourth derivative will be what? Sine x. So you can see the fourth derivative of f of x will be sine x. Or we know the fourth derivative of f of x of f of 0 would be what? 0. The fifth derivative of f of x will be cosine x. Or we know cosine of 0 also is what? 1. And the sixth derivative of f of x will be negative sine x, which means 0. And finally, would be the seventh derivative of f of x will be negative cosine x, and negative cosine of 0 is -1, right? So the derivative of sine x at 0 cycle through the value 0, 1, 0, -1, right? So now, we now construct the Taylor that approximate f of x is equal to sine x near 0. And we know p sub 1 of x, which will never change, is what? F of 0 plus f prime of 0 x minus 0. In this case, I need to write small. I see sub 1 of x will be just what? X, right? And then we will move to p sub 2. P sub 2 of x will be f of 0 plus f prime of 0 times x minus 0 plus the second derivative of f of 0 divided by 2 factorial times x minus 0 squared. So again, I'm not writing x minus 0 because you know x minus 0 is x. We know f prime of 0, we find this is 0, right? And we know this is 1, right? F double prime of 0 also is 0, so this will be 0. So I will left what? My p sub 2 of x will also be equal to x. We'll do the same thing for p sub 3. So you can see this will keep having, because p sub 3 of x will be what? f of 0 plus f prime of 0 times x minus 0. So I will just put x, right? Plus the second derivative of f of 0 divided by 2 factorial x minus 0 squared, which is x squared, right? Plus the third derivative of f of 0 divided by 3 factorial times x minus 0 cube, which is x to the power of 3. So if you check, we already know this would give us what? P sub 2 of x, which is what? Just x. And this one, the second derivative, the third derivative of f of 0, we find that's negative 1. So we'll have negative 1 divided by 3 factorial, which is negative 1 divided by 6, right? Times x to the power of 3. So this means 3 of x will be x minus 1 over 6x cubed. And that's the pattern we have to follow. So if I follow the same pattern, you can see we know P sub 4 of x would be what? P sub 3 of x, right? Then plus what? Because plus the fourth derivative of f of 0 divided by 4 factorial times x minus 0 to the power of 4. Or this one would be 0, right? Or we have this one, which is 0. We have find this, which is x minus 1 divided by 6x to the power of 3. So this means P sub 4 of x would be the same thing as P sub 3 of x, which is just x minus 1 divided by 6x to the power of 3. Right? So you see, same thing after the fourth P sub, so we'll be having the same cycle. So if I have to find P sub 5, look, we'll see some pattern in this case. That will give me what? P sub 4 of x plus the fifth derivative of f of 0 divided by 5 factorial times x minus 0 to the power of 5. We know this one. The fifth derivative of f of 0, we got 1. So we'll have 1 divided by 5 factorial. So this is 1 divided by 5 factorial times x to the power of 5. And we already have this p sub 4, which is x minus 1 over 6x to the power of 3, right? So this means my p sub 5 would be, so it would be x minus 1 divided by, if 6 times x cubed, then plus, let me use 5 factorial is 1 divided by 120. 5 factorial is 120, x to the power of 5. Believe you can guess p sub 5 and p sub 6 will be the same thing, right? Why? Again, because to find p sub 6 of x, it will just be p sub 5 of x plus the sixth derivative of f of 0 divided by 6 factorial times x to the power of 6. Or we can see the sixth derivative of f of 0 is what? 0. So this one would become 0. So we can see this is 0. So which means p sub 6 of x is equal to p sub 5 of x, which is what? X minus 1 divided by 6x to the power of 3 plus 120 x to the power of 5. Now finally, the last one, which is p sub 7, that will be what? P sub 6 of x plus the seventh derivative of f of 0 divided by 7 factorial times x to the power of 7. So the seventh derivative of f of 0 is negative 1. So this means my p sub 7 of x will be equal to x minus 1 divided by 6x to the power of 3 plus 1 divided by 120 x to the power of 5 minus 1 divided by, use a calculator to find 7 factorial, which is 5040 x to the power of 7. And that's it. Okay, so let's do this example as well. So on A, find the Taylor polynomials of order n is equal to 0, 1, 2, and 3 for f of x is equal to e to the power of x, center at 0. And part B, use the polynomial in part A to approximate e to the power of 1, point 1, and e to the power of negative 0.25. So again, this is, let's do part A first. So in part A, we know the coefficient of the Taylor polynomial center at 0 is what? C sub k is equal to the k derivative of f of 0 divided by k factorial. That's what we know, right? Look, it's right here, right? Because a is 0. So now, if that is the case, so we can go ahead we know with f of x is equal to e to the power of x. We can see what will be the kth derivative of f of x will still be what? E to the power of x. And we can see the kth derivative of f of 0 will always be what? 1. So this is just to show you, but like, you can do it step by step, but it's just to show you my c sub k will be what? 1 divided by k factorial for k is equal to 0, 1, 2, and 3, and so on. So they said for n is equal to 0. Give me 1 second, sorry. Okay, so no, sorry for this. So we can see P sub 0 of x will be what? F of 0, right? That's when n is 0, which is 1. P sub 1 of x, which will be f of 0 plus f prime of 0 times x minus 0. Don't forget, it's x minus 0 because the center is what? 0. If the center is not 0, you always write it down, okay? So that will give me what? So we know P sub 0 is 1, and P sub 1 is, P sub 0 of x is 1. P sub 1 of x will be 1 plus x, because f prime of 0 is 1, right? And P sub 2 of x will be equal to what? P sub 1 of x plus the second derivative of f of 0 divided by 2 factorial times x minus 0 squared, which means my P sub 2 of x will be 1 plus x squared divided by 2. And then finally, my P sub 3 of x, which will be what? P sub 2 of x plus the third derivative of f of 0 divided by 3 factorial times x minus 0 to the power of 3, which means my P sub 3 of x will be 1 plus x squared divided by 2 plus x cubed divided by 6, right? And then you can see if we follow this one, that's not a question that is asked. But if we follow this pattern, we can see what P sub n will just be, P sub n of x will just be what? 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial plus until plus x to the power of n divided by n factorial, which is equal to what? The sum from k is equal to 0 to n x to the power of k divided by k factorial. So this is what? The nth order Taylor polynomial of e to the power of x. So in case if you need it next, just know, you don't need to rewrite. If you can remember this one, it will save you time. So now next, we are asked to approximate, use the polynomial part A to approximate e to the power of 0.1 and e to the power of negative 0.25. So I'm going to use a table, okay, to represent this one. So I'm going to use a table. So I have n, all right? I have approximation. P sub n of 0.1. And then we have absolute error. You do remember that, right? And then my absolute error will be what? E to the power of 0.1 minus P sub n of 0.1. Then I will do the same thing for the approximation of negative 0.25, okay? And then we will do absolute error of that as well, which will be e to the power of negative 0.25 minus p sub n of negative 0.25. Okay. So now, if n is 0, right? Let me use blue. We know p sub n, p sub 0 of 0.1 will be 1, right? Based on right here. So it's not like I'm making up. P sub 0 of x is 1. So P sub 0.1 will still be 1. Okay, that's what I'm using. And then the absolute error will be what? E sub 0.1 minus 1, which will be 1.1 times 10 to the power of negative 1. Same thing if the error of negative point e to the power of negative 0.25, p sub 0 of negative 0.25 would still be 1. And e to the power of negative 0.25 minus 1 will be like 2.2 times 10 to the power of negative 1. When n is 1, p sub 1 of 0.1 will be 1.1. And the absolute error will be, use your calculator, 5.2 times 10 to the power of negative 3. And p sub 1 of negative 0.25 will be 0.75. And the absolute error of that will be 2.9 times 10 to the power of negative 2. Let's keep doing until when n is 2, we have, if you understand the step, you can just, speed this video and skip this part. So when n is 2, p sub 2 of 0.1 will be 1.105. And the absolute error will be 1.7 times 10 to the power of negative 4. And p sub 2 of negative 0.25 will be 0.78125. And that absolute error would be 2.4 times 10 to the power of negative 3. And then finally, when n is 3, 1.105167, and the error is 4.3 times 10 to the power of negative 6. And this is 0.778646. The error is 1.5 times 10 to the power of negative 4. And that's it. So again, that's it. And you can compare this value with, you can compare it to, if you check e to the power of 0.1, that's approximately 1.105. And if you check e to the power of negative 0.25, that is approximately 0.78. Okay, so that's for this. And again, I'm not going to solve all of this, but I will give you the hint so you can practice this one. So you are asked to use polynomial of order n is equal to 0, 1, 2, and 3 to approximate square root of 18. So in this case, you will set what? You will let, since this is a square root function, so you will let f of x be equal to square root of x. Okay? And then we need to choose a perfect square that is close to 18. So the perfect square close to 18 is 16, right? So we let the center, we choose the center. Choose the center A to be equal to 16. So from there we can see the Taylor polynomial have the form P sub n of x is equal to f of 16 plus f prime of 16 times x minus 16 plus the second derivative of f of 16 divided by 2 factorial times x minus 16 squared plus, and so on until what? The nth derivative of f of 16 divided by n factorial times x minus 16 to the power of n, right? So now, next, we know f of x is what? Square root of x. So that means f of 16 would be what? 4. F prime of x is 1/2 x to the power of negative 1/2, which means f prime of 16 will be equal to 1 divided by 8, Then the second derivative of x will be -1 divided by 4, x to the power of -3 divided by 2. So we will see the second derivative of f of 16 will be 1 divided by 256. And then finally, the third derivative of f of x will be equal to 3 divided by 8, x to the power of -5 divided by 2. So which means the third derivative of x will be 3 divided by 8192. Okay? So now I will let you fill out the table yourself, okay? So we will say therefore the polynomial P3, which include P0, P1, P2, so P0 of x will be 4, P1 of x will be 4 plus 1 over 8 times x minus 16. P sub 2 of x will be 4 plus 1 over 8 x minus 16 plus 1 divided by 16,000, sorry, 1 divided by 512, x minus 16 squared. Then finally, P sub 3 of x, which contain all of these three, 4 plus 1 over 8 x minus 16 plus 1 divided by 512 x minus 16 squared plus 1 divided by 16,384 x minus 16 cubed. Okay. So now it's for you. I will let you fill this table for the approximation, okay? So we have n, we have approximation, P sub n is equal to 18. Absolute error, which is square root of 18 minus P sub n of 18. So you use when n is 0, when n is 1, when n is 2, and when n is 3. And then Do not forget, square root of 18 is approximately what? Use your calculator, that is 4.24. I'm going to pause the video, fill out this, but do it yourself too. And this is the table I got. Pause the video, check with yours and see if it's the same thing. Now, let's talk about the remainder in a Taylor polynomial. Definition. Let P sub n be the Taylor polynomial of order n for f. The remainder in using P sub n to approximate f at the point x is R sub n of x is equal to f of x minus P sub n of x. We have the theorem for the remainder to Taylor. Let f ha have a continuous derivative up to the n plus 1th derivative of f on an open interval I containing a for all x in I. F of x is equal to P sub n of x plus R sub n of x, where P sub n is the nth order Taylor polynomial for f center at A, and the remainder is R sub n of x is equal to the n plus 1 derivative of f of c divided by n plus 1 factorial times x minus a to the power of n plus 1 for some point c between x and a. Okay, so I will bring this theorem down. Now, how do you estimate the remainder? Theorem. Let n be a fixed positive integer. Suppose there exists a number m such that n plus 1 derivative of f of c, absolute value of that is less than or equal to m. For all c between a and x inclusive, the remainder in the nth order Taylor polynomial for f centered at a satisfies the absolute value of R sub n of x is equal to absolute value of f of x minus P sub n of x, which is less than or equal to m times absolute value of x minus a to the power of n plus 1 divided by n plus 1 factorial. We'll do this example. Find a bound for the magnitude of the remainder for the Taylor polynomial of f of x is equal to cosine of x centered at 0. Okay. Okay, so let's do this. So you can see according to the remainder theorem, since the center A is equal to 0, we have sub n of x will just be n plus 1 derivative of f of c divided by n plus 1 factorial times x to the power of n plus 1 because a is 0, they said the center at 0. Again, you can see where C is a point between 0 and x. Also, we know that since f of x is what? Since f of x is equal to cosine x, right? Then we know the nth plus 1 derivative of c will either be plus or minus sine of c, or plus or minus, or the n plus 1 derivative of c will be plus or minus cosine of c, right? Depending on the value of n, right? But in all cases, either is plus or minus sine c or plus or minus cosine c, we know it will be less than or equal to we know absolute value of f of the n plus 1 derivative of f of c will be less than or equal to 1 because of sines and cosines, right? So therefore, we can take our m to what? We take m to be equal to 1 in the estimated remainder theorem. So we take m is equal to 1. Okay? So if we take m is equal to 1, theorem, so then and the absolute value of the remainder can be bounded as what? Absolute value of r sub n of x is equal to the absolute value of n plus 1 derivative of c divided by n plus 1 factorial times x to the power of n plus 1 should be less than or equal to absolute value of x to the power of n plus 1 divided by n plus 1 factorial. Okay, so you can approximate cosines of 0.1 using the Taylor polynomial of p sub 10, and the remainder will satisfy. You can check those, okay? So let's move to this example. Consider again the example in which we approximate square root of 18 using the Taylor polynomial. P sub 3 of x is equal to 4 plus 1 divided by 8x minus 16 plus minus 1 divided by 512 x minus 16 squared plus 1 divided by 16,384 times x minus 16 to the power of 3. Find an upper bound on the magnitude of the remainder using p sub 3 of x to approximate square root of 18. So, of course, we can see in this problem, we have n is 3, right? A is 16, and x is what? 18. So we found that the remainder approximating square root of 18 by p sub 3 of 18 satisfies the bound r sub 3, absolute value of r sub 3 of x, 18, not x, 18 should be less than or equal to what? M times x is 18, right? Is x minus a, so 18 minus 16 to the power of 4 divided by 4 factorial, which will give me what? 2 divided by 3 times m, right? Where m is a number that satisfies absolute value of the fourth derivative of c should be less than or equal to m. For all c between 16 and 18 inclusive, right? So we can see in this particular problem, we find that we can see the fourth derivative. You can do this one yourself, okay? We have, on the previous one, we have the third derivative. So we have the fourth derivative of c would be equal to what? Negative 15 divided by 16 c to the power of negative 7 divided by 3. Parentheses, we have already found the fourth derivative of x is negative 15 divided by 16 times x to the power of negative 7 over 2, right? So m must be chosen as small as possible, right? Such that absolute value of the fourth derivative of f of c should be equal to 15 divided by 16 c to the power of negative 7 over 2, which is equal to 15 divided by 16c to the power of 7 over 2 should be what? Less than or equal to m. For 16 less than or equal to c, and c is less than or equal to 18. Or you can verify that. You can see or 15 divided by 16c to the power of 7 divided by 2 is a decreasing function of c on the closed interval 16 to 18. And if you check n, you can use your calculus one, you will see the maximum and has a maximum value if you of approximation (5.7) times 10 to the power of -5 at c is equal to 16. It's because when c is equal to 16, that's when you have a maximum. So therefore, a bound on the remainder is absolute value of R3 of 18 should be less than or equal to 2 divided by 3 times m, which is approximately 2 divided by 3 times 5.7 times 10 to the power of -3. And that is approximately 3.8 times 10 to the power of -5. Okay, we'll stop this right here, and I will see you in the next section.